Oberleutnant Hans Becker, commander of a Panzer III medium tank in the 2nd Panzer Division, woke up on the morning of November 30th, 1941, inside his tank where he and his crew had spent the night huddled together for warmth after another day of failed attempts to advance toward Moscow through increasingly heavy Soviet resistance and worsening winter conditions. The temperature inside the steel hull was barely above freezing, despite the body heat of 5 men packed into the cramped crew compartment, and when Becker tried to move his legs to climb up to the commander's cupola, he found that his boots had frozen solid to the metal floor during the night, and he had to work them free carefully to avoid leaving the leather stuck to the ice that had formed from condensation and frozen breath. He pushed open the turret hatch, expecting another miserably cold but otherwise normal morning of preparing the tank for the day's operations, and what he saw outside made his blood run cold in a way that had nothing to do with the temperature. The entire Panzer Company, 15 tanks that had been parked in a rough defensive circle the previous evening, looked like they had been transformed overnight into sculptures carved from solid ice, with thick layers of frost covering every external surface and long icicles hanging from gun barrels, track guards, and external equipment bins. The temperature had dropped during the night from -20 degrees Celsius to -35 degrees, and this sudden plunge into extreme cold had created conditions that German tanks simply were not designed to handle. The petroleum-based engine oils and hydraulic fluids that the Wehrmacht used in its armored vehicles had been selected for European conditions where winter temperatures rarely dropped below -10 degrees, and these lubricants would begin to thicken and lose their flow characteristics at -20 degrees, becoming almost solid at -30 degrees, transforming into waxy substances that prevented engines from turning over, transmissions from engaging, and turrets from rotating on their bearings. Becker climbed down from his tank and walked around the vehicle performing his standard pre-operation inspection, and with each step, his sense of dread increased as he discovered more and more systems that had been rendered completely non-functional by the extreme cold. The engine oil dipstick came out covered in a yellowish wax that had no resemblance to the thin flowing liquid that should have been lubricating the engine's moving parts. The coolant in the radiator had frozen despite being mixed with antifreeze, because the antifreeze concentration had been calculated for European winter temperatures and was completely inadequate for Russian conditions, and the expansion of freezing water had cracked the radiator core and fractured several coolant lines that would need to be replaced before the engine could be operated again. The track tensioning springs had contracted in the cold and allowed the tracks to sag loose on their road wheels, and attempting to move the tank in this condition would almost certainly throw a track within the first few meters of travel. The 5-centimeter main gun that was the Panzer III's primary weapon had its breech mechanism frozen solid, with the recoil fluid that cushioned the gun's rearward movement after firing having thickened into a gel that would prevent the gun from firing even if a round could be loaded into the chamber, which it could not because the loading mechanism's springs and linkages were also frozen in place and could not be moved by human strength alone. The radio equipment that allowed the tank to communicate with other vehicles in the company and with higher headquarters had suffered moisture condensation during the night that had then frozen inside the radio chassis, potentially damaging delicate vacuum tubes and crystal oscillators in ways that might not be repairable in the field. The optical gun sight that the gunner used to aim the main weapon had its lenses fogged and frost-covered in a way that made precision aiming impossible, and attempting to clear the frost by breathing on the lenses or wiping them with cloth only created more moisture that would immediately refreeze. Becker's tank was not unique in suffering these problems, but was rather typical of the condition affecting every single tank in the company, and indeed most of the tanks across the entire Eastern Front on that November morning, when temperature dropped to levels that German military planners had simply never considered possible, and that German equipment manufacturers had never designed their products to withstand. The 2nd Panzer Division, which had begun Operation Barbarossa in June with over 200 operational tanks, and which had fought its way across 1,000 kilometers of Soviet territory while maintaining reasonable mechanical readiness rates through proper maintenance and adequate supplies of spare parts and lubricants, now found itself with less than 50 tanks that could actually move under their own power. And even these 50 machines were operating at severely degraded performance levels with engines that struggled to develop even half their rated horsepower and transmissions that shifted gears only with great difficulty and grinding noises that indicated imminent mechanical failure. The German panzer forces on the Moscow front included approximately 1,000 tanks distributed among multiple panzer divisions and independent tank battalions, and the overnight temperature drop to -35 degrees had rendered approximately 2/3 of these vehicles completely immobile, and the remaining 1/3 only marginally operational with severely degraded combat effectiveness. This sudden catastrophic loss of armored striking power could not have come at a worse time from the German perspective, because Soviet forces were preparing to launch their winter counteroffensive, and the panzer divisions represented the Wehrmacht's primary mobile reserve that could respond to Soviet breakthroughs and conduct counterattacks to restore defensive lines that were already under severe pressure from Soviet probing attacks that were testing German defenses in preparation for the major offensive that Marshal Zhukov was planning to launch within days. Tank crews across the front attempted every improvised solution they could think of to get their vehicles operational again, with the most common approach being to light fires underneath the tanks, in hopes of warming the engine enough to allow the oil to flow and the engine to turn over. This technique had been used successfully during less severe cold snaps earlier in the autumn, when temperatures had dropped to -10 or -15 degrees, and warming the engine for 30 to 45 minutes with careful fires using whatever fuel could be scrounged from local sources had usually been sufficient to raise metal temperatures enough to allow starting. But at -35 degrees, the amount of heating required to warm a 30-ton tank to operating temperature was far beyond what could be achieved with small fires, and attempts to use larger fires risked damaging the tank's fuel tanks, ammunition storage, or other flammable components that could explode or catch fire if heated too much. Some tank crews did experience exactly these catastrophic failures when their heating fires got out of control, or when gasoline fumes from leaking fuel lines were ignited by flames that were supposed to be warming the engine, but which instead turned the tank into a fireball that killed crew members who were standing too close, or who were inside the tank trying to start the engine at the moment when fuel vapors ignited. The exact number of German tanks lost to fires caused by desperate attempts to de-ice frozen vehicles is not precisely documented, but post-war analysis suggests that dozens and possibly over 100 tanks were destroyed or damaged beyond field repair by fires that started as controlled heating attempts, but which escalated into disasters when frozen fuel lines cracked under thermal stress, or when fuel tanks that had contracted in the cold suddenly leaked when heated rapidly. The Panzer III and Panzer IV tanks that formed the backbone of German armored forces in 1941 were sophisticated machines for their era, incorporating cutting-edge automotive engineering, advanced fire control systems, and carefully designed crew ergonomics that made them among the most effective tanks in the world when operated under the conditions they had been designed for. But none of these design considerations had included operation in temperatures below -20 degrees Celsius for extended periods, and the engineers at Daimler-Benz, MAN, and other German manufacturers who had designed these vehicles had based their specifications on European climate data that simply did not include the extreme continental cold of the Russian interior during winter. The result was that virtually every fluid system, mechanical linkage, electrical component, and rubber seal on a German tank would fail or operate at severely degraded efficiency when exposed to temperatures below -30 degrees, creating a cascade of mechanical problems that rendered these otherwise excellent fighting vehicles completely useless. The engine cooling systems on German tanks used a mixture of water and ethylene glycol antifreeze, with the antifreeze concentration calculated to prevent freezing down to approximately minus 25 degrees Celsius, which had been considered adequate for any realistic operational scenario in Europe. But at minus 35 degrees, this antifreeze mixture was insufficient, and the coolant would begin to form ice crystals that could block circulation passages and cause local freezing in areas where coolant flow was restricted. The expansion of freezing coolant created enormous pressures inside closed cooling systems, pressures that were sufficient to crack cast iron engine blocks, fracture aluminum radiator cores, and burst rubber hoses that became brittle and inflexible in extreme cold. Once an engine block cracked from freezing coolant, that engine was essentially destroyed and would require complete replacement, a repair operation that was far beyond the capabilities of field maintenance units, and that required the tank to be shipped back to depot-level facilities in Germany where new engines could be installed. The transmission and final drive systems on German tanks used heavy gear oils that were designed to remain viscous enough at normal operating temperatures to provide adequate lubrication for gears and bearings, while also remaining thin enough to allow easy shifting between gears. At minus 35 degrees, these gear oils would thicken dramatically, increasing their viscosity by factors of 10 or more compared to normal operating conditions, creating enormous resistance to gear rotation and making gear shifting nearly impossible even when the engine could generate enough power to overcome the resistance. Tank drivers attempting to shift gears in these conditions would find that the shift lever simply would not move despite applying all their strength. And forcing the shift could break shift forks, strip gear teeth, or crack transmission cases that had become brittle from the cold. The track systems on German tanks consisted of steel track links connected by pins and bushings that needed to articulate smoothly as the track rotated around the drive sprocket, road wheels, and return rollers. And this articulation required that the pins and bushings maintain a small amount of clearance to allow relative motion while also remaining tight enough to prevent excessive play that would cause accelerated wear. At minus 35 degrees, the steel components of the track would contract differently than the bronze bushings, creating clearances that were either too tight for smooth operation or too loose, and allowing the track to bind or skip off the drive sprocket teeth. Additionally, any mud or water that had gotten into the track during the previous day's operations would freeze solid overnight, effectively welding the track links together into a solid frozen mass that the engine could not possibly move, even if it could be started. The electrical systems on German tanks, including the starter motors that turned the engine over for starting, the generators that recharged the batteries and provided power for radios and turret traverse motors, and the various switches and relays that controlled different vehicle functions, all suffered from cold-related failures that compounded the mechanical problems affecting the tank's mobility. The lead-acid batteries that provided electrical power for starting had their capacity reduced by 50% or more at minus 35 degrees compared to their rated capacity at room temperature, meaning that batteries that were fully charged might have just enough power for 1 or 2 starting attempts before being completely drained. And if those attempts failed because of other cold-related problems, the tank would be left without electrical power until the batteries could be removed, taken to a heated shelter, warmed up slowly to avoid cracking the cases, and then recharged over a period of several hours. Tank crews who found themselves unable to start their vehicles through normal procedures sometimes attempted to start their engines by towing the tank with another vehicle or by using hand cranks if the tank was equipped with a manual starting system. But these alternative starting methods were problematic at best and dangerous at worst when attempted in extreme cold conditions. Tow starting required another vehicle that was operational, which was increasingly unlikely as more and more vehicles suffered cold-related failures, and the technique required careful coordination between the towing vehicle and the tank being towed to avoid damaging transmission components or breaking tow cables that became brittle in extreme cold. Hand cranking was possible on some tank models, but required enormous physical effort to turn the crankshaft of a cold engine whose oil had turned to wax, and several tank crews suffered serious injuries when hand cranks kicked back unexpectedly as engines misfired, or when frozen components suddenly broke free and released stored energy that could strike crew members with potentially lethal force. The German Army had begun manufacturing winter lubricants and antifreeze in late 1941, once the extent of the cold weather problems became apparent. But these specialized cold weather fluids were not available in sufficient quantities to reservice all the tanks on the Eastern Front until well into December and January, by which time the worst of the mechanical crisis had passed, as temperatures moderated slightly, and as Soviet counteroffensives had already achieved significant breakthroughs that fundamentally altered the tactical situation. Even when winter-grade lubricants did become available, changing all the fluids in a tank was a time-consuming maintenance procedure that required draining the old oil from the engine, transmission, and final drives, flushing the systems to remove residual summer-grade lubricant, and refilling with the appropriate quantities of winter-grade fluids, all while working in conditions that made even simple maintenance tasks difficult and dangerous, as tools would stick to bare skin, metal components would shatter if struck with normal force, and crew members risked frostbite if they removed their gloves to perform fine manipulations that required good tactile feedback. The Soviet T-34 medium tank, which the Germans had first encountered during the summer campaign and which had proven superior to German tanks in several important respects, including armor protection, gun power, and mobility, demonstrated much better cold weather performance than German tanks because Soviet engineers had specifically designed the T-34 for winter operations in the Russian climate. The T-34 used a diesel engine rather than the gasoline engines used in most German tanks, and diesel fuel was less volatile and less prone to forming explosive vapors than gasoline, making diesel engines safer to warm with external fires. The T-34's wide tracks distributed the tank's weight over a larger surface area, reducing ground pressure and preventing the tank from sinking into snow or mud that would bog down narrow-tracked German vehicles. The T-34's simple mechanical design with large clearances and relatively crude but robust construction meant that the tank could tolerate much greater thermal expansion and contraction without suffering binding or fractures that would disable more precisely engineered German tanks. Soviet tank crews also had access to winter-grade lubricants that had been stockpiled in advance of the winter campaign, whereas German forces were dependent on supply lines stretching back over 1,000 kilometers to Germany and Poland, and these supply lines were constantly being interdicted by Soviet partisan forces who specifically targeted fuel and lubricant shipments, knowing that depriving German armor of these essential fluids would render the Panzer division's combat ineffective without having to fight them in direct combat. The combination of Soviet superiority in cold weather tank design, availability of appropriate lubricants and antifreeze, and extensive experience with winter operations gave Red Army armored units a decisive advantage during the winter campaign that helped enable the successful counteroffensive that pushed German forces back from Moscow and inflicted catastrophic losses on Wehrmacht units that had seemed unstoppable during the summer and autumn months. General Heinz Guderian, commander of 2nd Panzer Army on the southern flank of the Moscow front, reported to Army Group headquarters in early December that his armored strength had been reduced from over 300 operational tanks at the beginning of November to fewer than 70 operational tanks by mid-December, with the majority of losses being mechanical failures caused by cold weather rather than combat damage from Soviet anti-tank weapons. Guderian's desperate requests for winter lubricants, antifreeze, and spare parts to repair cold-damaged engines went largely unfulfilled because the Wehrmacht logistics system was already strained beyond capacity simply trying to deliver basic necessities like food and ammunition to frontline units, and specialized items like winter-grade oils and replacement engine blocks were simply not available in the quantities needed to restore German armored strength to acceptable levels. The immobilization of German armor had immediate tactical consequences as Soviet counterattacks that began on December 5th encountered Wehrmacht defensive lines that lacked the mobile reserves needed to respond to breakthroughs and restore broken defensive positions. In previous campaigns, German commanders had relied on their Panzer divisions to serve as fire brigades that could be rushed to threatened sectors and conduct counterattacks that would seal off Soviet penetrations before they could be exploited into operational-level breakthroughs. But this tactical concept was completely impossible when the Panzer divisions themselves were immobilized and unable to move to where they were needed most. Soviet commanders quickly recognized that German armor was largely absent from the battlefield and adjusted their tactics accordingly, pressing attacks in sectors where they knew German infantry would have no armored support, and exploiting breakthroughs with their own tank units that were operating effectively despite the cold weather. Tank crews who found themselves trapped inside immobilized vehicles faced difficult decisions about whether to remain with their tanks in hopes of eventually getting them operational again, or to abandon the vehicles and join infantry units that were fighting defensive battles without armored support. The official Wehrmacht policy was that tank crews should never abandon their vehicles except under direct enemy threat. But this policy had been developed for situations where tanks were disabled by combat damage rather than mechanical failure, and it made little sense to keep five-man tank crews sitting inside frozen vehicles that could not contribute to the defense when those same crews could be fighting as infantry with rifles and machine guns. However, abandoning tanks without authorization could result in court-martial for cowardice or dereliction of duty, creating a catch-22 situation where crews could be punished for staying with useless vehicles or punished for leaving them to join the actual fighting. The psychological impact on German tank crews of watching their sophisticated and powerful fighting vehicles transform overnight into useless frozen metal boxes was profound and long-lasting, with many veterans of the Winter Campaign later describing their feelings of helplessness and frustration as they performed maintenance procedures that should have had their tanks operational within hours, but which had no effect whatsoever because the cold was simply too severe for any field-expedient solutions to overcome. Tank commanders who had led their vehicles across hundreds of kilometers of Soviet territory during the summer, destroying enemy tanks and bunkers and supporting infantry attacks with accurate fire and mobile maneuver, now found themselves sitting in command cupolas, unable to start engines or traverse turrets or operate weapons, reduced to the role of passive observers as Soviet forces attacked positions that desperately needed armored support that could not be provided because the tools and machines that should have provided that support were frozen solid and non-functional. The German tank recovery and repair organizations were completely overwhelmed by the scale of mechanical failures that occurred during late November and early December 1941, with recovery vehicles themselves experiencing the same cold-related problems that affected combat tanks, and with repair facilities lacking the heated workshops and specialized tools needed to perform complex engine and transmission repairs in winter conditions. Standard recovery procedures involved towing disabled tanks back to field maintenance shops where trained mechanics could diagnose problems and perform repairs. But when hundreds of tanks needed recovery simultaneously, and when recovery vehicles could barely operate themselves, the entire system collapsed, and tanks had to be abandoned in place where they had broken down, often being destroyed by their own crews to prevent capture, when Soviet forces overran the positions where the disabled vehicles were located. The Wehrmacht maintenance doctrine emphasized keeping tanks operational through preventive maintenance and quick repairs performed by unit-level mechanics using a modular approach where defective components like engines or transmissions could be removed as complete assemblies, and replaced with spares from a stockpile maintained at higher echelons. But this system required that spare components be available in adequate numbers and that the repair facilities and tools needed for component replacement be functional and accessible. Neither of these conditions existed during the winter crisis, with spare component stocks having been exhausted by 6 months of continuous combat operations, and with repair facilities being unable to operate effectively in extreme cold because their workshops were not heated, and their tools and equipment were subject to the same cold-related failures that affected combat vehicles. Some Panzer divisions attempted to consolidate their remaining operational tanks into composite battalions that could at least provide some armored support to defensive operations, combining vehicles from multiple companies and even multiple regiments into ad hoc units that might have 15 or 20 functional tanks, rather than the hundreds that the division should have possessed at full strength. These composite units operated under enormous disadvantages, including unfamiliar command relationships, crews that had not trained together, and mixture of different tank models with different performance characteristics and ammunition requirements, but they represented the only available option for maintaining any armored capability whatsoever during the crisis period, when new tanks could not be delivered from Germany, and when existing tanks could not be repaired in the field. The longer-term strategic implications of the tank immobilization crisis extended far beyond the immediate tactical problems of winter 1941 through 42, because the tanks that were lost to cold-related damage represented irreplaceable assets that German industry could not quickly replace, given the enormous demands on manufacturing capacity from multiple fronts and weapon systems. Germany produced approximately 5,000 tanks during all of 1941, with significant portions of this production going to units in North Africa, the Balkans, and Western Europe, leaving relatively few replacement vehicles available for the Eastern Front, where losses from both combat and mechanical failure were highest. The sudden loss of over 1,000 tanks to cold-weather mechanical failure during a single winter month was equivalent to losing more than 20% of Germany's entire annual tank production. And this loss came at a time when Germany needed to maintain large armored forces in Russia to contain Soviet counteroffensives while also defending against potential British operations in the West and maintaining forces in occupied territories throughout Europe. The lessons learned from the winter tank crisis of 1941 influenced German tank design and operational doctrine for the remainder of the war, with subsequent tank models like the Panther and Tiger incorporating design features intended to improve cold-weather performance, including better sealing of crew compartments to prevent moisture infiltration, improved heating systems for crew comfort and equipment functionality, and consideration of extreme temperature operation in the selection of lubricants and fluids used throughout the vehicle. However, these design improvements came too late to affect the outcome of the war on the Eastern Front, where the damage to German armored strength caused by the winter of 1941 had already shifted the correlation of forces permanently in favor of the Soviet Union, and where German tank production could never match Soviet tank production even when German tanks were technically superior on a per-vehicle basis. The German experience with frozen tanks in winter 1941 also highlighted fundamental problems with Wehrmacht logistics and supply planning that reflected deeper strategic failures in Germany's approach to the war with the Soviet Union. The assumption that Operation Barbarossa would conclude before winter meant that German military planners had not prepared adequate stocks of winter equipment, including not just cold-weather clothing for troops, but also specialized lubricants, antifreeze, and other materials needed to maintain mechanical equipment in extreme cold. When winter arrived, and the campaign had not concluded, German forces found themselves operating in conditions they were not equipped for, with predictable catastrophic results that could have been avoided if proper planning had been conducted and if German leaders had been willing to consider the possibility that their optimistic assumptions about Soviet collapse might prove wrong. The contrast between German and Soviet tank performance during winter 1941 provides an instructive case study in the importance of designing military equipment for the actual operating environment rather than for idealized conditions that may not reflect operational reality. Soviet tanks were designed by engineers who understood that their vehicles would need to operate in Russian winter conditions, and who therefore made design choices that prioritized cold weather reliability, even when those choices meant accepting other trade-offs like reduced precision in manufacturing tolerances or simpler but less sophisticated mechanical systems. German tanks were designed by engineers who prioritized performance characteristics like armor protection, firepower, and automotive performance under ideal conditions, but who did not adequately consider how those performance characteristics would degrade in extreme environments that were outside the design envelope. The winter tank crisis also demonstrated the vulnerability of complex mechanical systems to environmental extremes that could disable them more effectively than enemy action, a lesson that has implications far beyond World War II and that remains relevant for modern military forces operating in extreme climates. Modern tanks are far more sophisticated than their World War II predecessors and incorporate advanced technologies like composite armor, thermal imaging sights, digital fire control computers, and gas turbine engines, but these sophisticated systems are also potentially more vulnerable to environmental conditions if they have not been properly designed and tested for extreme cold or heat. Military forces planning to operate in Arctic or desert environments must ensure that their equipment has been designed specifically for those conditions, and that maintenance crews have the training and equipment needed to keep complex systems operational despite environmental challenges. The human dimension of the frozen tank crisis should not be overlooked in discussions of mechanical failures and logistics breakdowns, because behind every immobilized tank were 5 crew members who had depended on that vehicle for mobility, firepower, and protection, and who now found themselves essentially disarmed and vulnerable in the middle of a winter battlefield where Soviet forces held the initiative and where German defensive positions were collapsing under pressure from attacks that German armored reserves could not counter, because those reserves were frozen in place and unable to move. Tank crews who had taken justifiable pride in their vehicles and their skills as armored warriors now experienced the humiliation and frustration of helplessness. Watching their tanks transform from powerful weapons into useless steel boxes that could not defend themselves or support the infantry who desperately needed armored support. The winter of 1941 marked the end of the period when German panzer divisions could claim to be the most effective armored force in the world, because the combination of heavy combat losses during the summer and autumn campaign and catastrophic mechanical failures during the winter had reduced German armored strength to levels from which it would never fully recover. While Germany would produce new and more powerful tank models in subsequent years and would occasionally achieve impressive tactical victories through superior crew training and tactics, the Wehrmacht would never again possess the kind of overwhelming armored superiority that it had enjoyed during the early years of the war, when its panzer divisions could break through enemy defensive lines and conduct deep exploitation operations that paralyzed opposing armies and led to their rapid collapse. The Soviet Red Army, by contrast, emerged from the winter campaign with growing confidence in its ability to match and eventually surpass German armored capabilities, having demonstrated during the Moscow counteroffensive that Soviet tanks could operate effectively in conditions that completely paralyzed German armor, and having inflicted heavy losses on German panzer divisions through a combination of direct combat and exploitation of German mechanical failures. The T-34 tank, which had been produced in relatively small numbers during 1941, would become the most produced tank in history, with over 80,000 built during the war years, and this enormous quantitative superiority, combined with the T-34's proven cold weather reliability, would give the Soviet Union a decisive advantage in armored warfare that would eventually enable the Red Army to drive German forces back to Berlin. The night when German tanks turned into 300-ton ice blocks represents one of the most significant but least appreciated turning points of World War II, because mechanical failure achieved what Soviet anti-tank guns and mines had been unable to accomplish during 6 months of combat. The near-complete neutralization of German armored striking power at a critical moment when that striking power was desperately needed to contain Soviet counterattacks and prevent the collapse of German defensive lines around Moscow. The frozen tanks scattered across the Russian landscape in December 1941 bore silent testimony to the power of nature to determine military outcomes regardless of human plans or technological sophistication, and their immobilization marked the beginning of the end for German hopes of defeating the Soviet Union and winning the war in the East. The veterans who survived the winter tank crisis carried memories of that terrible period for the rest of their lives, remembering the frustration of trying every possible technique to start frozen engines, the desperation of lighting fires under tanks, knowing the risks of explosion or fire, the helplessness of watching Soviet attacks develop without being able to respond with armored counterattacks, and the ultimate humiliation of having to abandon sophisticated fighting machines that had carried them across thousands of kilometers of enemy territory, but which could not function when temperatures dropped below the limits their designers had never considered possible. These memories shaped post-war German military thinking about equipment design, logistics planning, and the importance of preparing for worst-case environmental conditions, rather than assuming that operations would always occur under ideal circumstances. The frozen tanks of winter 1941 remain as monuments to the dangers of technological overconfidence and inadequate planning for extreme conditions, and they serve as permanent reminders that even the most sophisticated military equipment can become useless when operated outside its design envelope, and that mechanical reliability in extreme environments is just as important as firepower, armor protection, or mobility under ideal conditions. The 3,000 German tanks that became immobilized during late November and early December 1941 could have changed the outcome of the Moscow campaign if they had been able to function, but their transformation into frozen metal sculptures ensured that the Wehrmacht's last chance to defeat the Soviet Union before the correlation of forces shifted decisively against Germany was lost forever in the Russian winter. The modern militaries that study the German tank crisis of winter 1941 focus particular attention on the relationship between equipment design specifications and actual operational requirements, recognizing that equipment must be tested and validated for the full range of environmental conditions it might encounter in combat, rather than for idealized conditions that exist only in laboratory settings or peacetime exercises. The United States military learned this lesson during the Korean War, when American tanks and other vehicles experienced cold weather failures, similar to those suffered by German forces in Russia, leading to comprehensive redesign of cold weather lubricants and antifreeze formulations and extensive Arctic testing programs to ensure that American military equipment could function in extreme cold environments. NATO forces maintain specialized Arctic warfare units that train regularly in Norway, Canada, and Alaska, and these units use equipment specifically designed and tested for sub-zero operation to ensure that the mistakes made by German planners in 1941 are not repeated. The German tank industry attempted to respond to the winter crisis by developing winterization kits that could be retrofitted to existing tanks, including improved engine heaters, better insulation for crew compartments, special cold weather lubricants and fluids, and modified starting systems that would function more reliably at low temperatures. These winterization kits began reaching frontline units in late winter and early spring of 1942. But by that time, the immediate crisis had passed, as temperatures moderated and as the Wehrmacht had already lost its chance to capture Moscow and defeat the Soviet Union before American entry into the war transformed the strategic balance decisively against Germany. The winterization improvements helped German tanks operate more effectively in subsequent winter campaigns, but they could not compensate for the fundamental strategic errors that had led to the winter 1941 crisis, or for the enormous losses of men and equipment that had been suffered during that terrible winter. The Soviet Union's success in maintaining tank operations during winter 1941 provided valuable experience that would be applied throughout the remainder of the war, and during the Cold War period, when Soviet military doctrine emphasized the ability to conduct large-scale armored operations in all weather conditions, including the severe continental winters that characterized much of the potential battlefield in Eastern Europe. Soviet tank designers continued to prioritize cold weather reliability in subsequent tank models, including the T-54, T-55, T-62, and T-72 series that formed the backbone of Soviet and Warsaw Pact armored forces throughout the Cold War. And this emphasis on environmental reliability gave Soviet armor a reputation for ruggedness and dependability, even when individual vehicles might lack the sophisticated fire control systems or armor protection of Western tanks. The psychological legacy of the frozen tank crisis affected German armored forces throughout the remainder of the war, creating a lingering anxiety among Panzer crews about whether their vehicles would function when needed most, and whether environmental conditions might disable them just as effectively as enemy fire. This anxiety was not entirely irrational, given that German tanks continued to experience higher mechanical failure rates than Soviet tanks throughout the war, with sophisticated German designs being more prone to break down than simpler Soviet designs that had been engineered from the beginning to tolerate abuse and adverse conditions. German tank crews learned to perform extensive preventive maintenance and to carry additional spare parts and tools that might not have been officially authorized, but which experience had taught them would be necessary to keep their vehicles operational under field conditions. The winter 1941 tank crisis demonstrated that logistics and maintenance capabilities are just as important as combat capabilities in determining armored force effectiveness. Because tanks that cannot be kept operational due to inadequate supplies of lubricants, spare parts, or qualified maintenance personnel are just as useless as tanks that have been destroyed by enemy fire. Modern military forces invest heavily in logistics and maintenance organizations that can sustain complex mechanical systems in forward-deployed locations, recognizing that the most capable weapon systems in the world become worthless if they cannot be maintained in operational condition throughout extended campaigns in challenging environments. The German failure to provide adequate logistics support for winter operations in Russia stands as a permanent reminder of what happens when military planners focus exclusively on combat capabilities while neglecting the mundane but essential functions of supply and maintenance that enable combat forces to remain effective over time. The frozen tanks of winter 1941 remain a powerful symbol of how environmental factors can overwhelm technological superiority and render sophisticated weapon systems completely ineffective, reminding military planners and equipment designers that engineering excellence must include consideration of worst-case operating conditions, and that equipment specifications must reflect actual operational requirements, rather than idealized assumptions about how and where that equipment might be used. The 3,000 German tanks that became frozen metal sculptures during a single week in late November and early December 1941 could have altered the course of the war if they had been able to function. But their failure to operate in extreme cold ensured that German hopes of decisive victory in the East would never be realized, and that the Wehrmacht would spend the next 3.5 years fighting a losing defensive campaign against an opponent whose equipment, while often technically inferior, proved far better suited to the actual conditions of warfare on the Eastern Front.